Good morning, everyone. Thank you for coming to my presentation. My name is Chen, and today I'll be presenting our work, Modeling Control Traffic in Software-Defined Networks. So in an SDN, control traffic is very important because it is how the network controller keeps track of and manages the state of the entire network. Control type messages are used to manage and monitor SDN devices, and they can be used to configure flow rules, allocate queues, and even to pull device statistics such as flow rule usage and port usage. In this work, we observe and analyze two SDN control traffic protocols, first of which is OpenFlow. OpenFlow is used by the controller to access and modify network devices forwarding planes. For example, using OpenFlow, a controller can add, delete, or modify flow rules, and can even query the device's forwarding plane statistics. For example, the controller can query statistics such as the size of the flow tables, the durations of each flow rule, or even the number of packets that each flow rule has matched with. The other SDN protocol that we observe and analyze is OVSDB, which stands for Open vSwitch Database Management Protocol. Although originally designed for use with the Open vSwitch, other switch manufacturers also started supporting this protocol, and now it has become an industry standard management protocol. OVSDB allows a controller to manage the non-forwarding plane components of the switch. In this sense, while OpenFlow is for flow manipulation, OVSDB is the manipulation of the machine state itself. For example, OVSDB can be used to configure priority queues, set up bandwidth slicing parameters on each queue, or even do management tasks such as bringing a port down or bringing a port up. Control traffic in SDN is especially important for two main reasons. First, the speed of control traffic message delivery is directly correlated to network responsiveness. For example, in edge and fog networking scenarios, fast control message delivery will result in quick service configurations. Second, the control traffic consumes link bandwidth in the network. Control traffic directly competes with data traffic for available bandwidth and adds additional traffic to the entire network. In this sense, having less control traffic is better for the network, so that it consumes less bandwidth. Knowledge of control traffic in the SDN is very important, but existing literature tends to fall short when it comes to describing control traffic characteristics. There are works that analyze and acknowledge the presence of control traffic in SDN environments, but these analyses usually rely on abstracted or incomplete control traffic measurements and do not offer any models for control traffic prediction. For example, these works usually either assume that control traffic and data traffic are completely separate and do not interact, or they make simplified assumptions about control traffic patterns that aren't representative of real-world data. For example, they use fixed rates for control traffic patterns, whereas in the real world, these rates are wildly variable. Furthermore, these works tend to analyze control traffic from an observational perspective and do not present models for control traffic prediction. In experiments with SDN testbeds, we observed two main types of control traffic between the switch and the controller. The first type of messages is the flow rule installation messages. These are messages that are sent from the controller to the switch in order to install new flow rules onto those switches. Second type of messages would be statistics polling messages. These messages are the kind of messages that are sent between the controller and the switch in order for the controller to maintain an updated view of the entire network. Next, we'll describe both types of control traffic, and we'll describe our observations of them in a real testbed. First, we will discuss control traffic patterns associated with flow rule installations. Flow rule installation control traffic is very important to analyze because in large dynamic networks, each switch will be installing hundreds of new flow rules each second, which will result in hundreds of these flow rule messages each second. There are two main types of flow rule installation patterns, proactive and reactive flow rule installations. In proactive flow rule installation scenarios, the controller already knows ahead of time what type of flows that each switch will encounter, and as such will be able to install new flow rules preemptively. One example of this would be in resource allocation scenarios, where the request for resources already went to the controller first, so it already knows what type of traffic the network is going to encounter. In this type of scenario, all that is needed is one flow mod packet is all that is needed to install the flow rule correctly. The second type of flow rule installation scenario is the reactive flow rule installation. This scenario happens when the switch receives a packet that does not match any of its flow rules and now must consult with the controller about what to do with this packet. This type of scenario incurs a large control traffic penalty, as there are now two packets that must be exchanged between the controller and the switch. The first packet would be the packet in message that is sent from the switch to the controller. This informs the controller of the packet that doesn't match any flow rules, and these packet messages can be up to 600 bytes large, depending on what type of packet that has triggered the packet message. Once the controller has received the packet message and has made a decision about what to do, the controller will then respond with a flow mod message to the switch. This flow mod message installs a new flow rule onto that switch, and after that, then the flow rule is correctly installed. In both reactive and proactive flow rule installation scenarios, a flow mod message is sent from the controller to the switch to install a new flow rule or to modify an existing flow rule. When characterizing control traffic, one thing to take into account is the size of these messages. Depending on the flow rule complexity, the size of flow mod messages can vary significantly in size. For example, if the flow rule only has one match field, the flow mod packet will be relatively small, while if you have many match fields, the flow rule packet can grow in size. When it comes to predicting control traffic throughput, the type of flow rule configurations must also be taken into account. Next, we will discuss control traffic patterns associated with polling the statistics of each switch. For a network controller to keep track of what is going on in the network, it must periodically receive updates about the status of each of the switches in the network. The switch statistics polling is accomplished through the multi-part request and multi-part reply messages of the OpenFlow protocol. Since each multi-part request and multi-part reply message will only convey the statistics of one specific part of the switch to the controller, if the controller wants to query the complete state of the switch, it must send multiple multi-part request messages to the switch. For example, there will be a separate multi-part request message for flow table statistics, flow rule statistics, and queue statistics. The multi-part request messages are fixed in size, but depending on the state of the switch, the multi-part reply messages will vary in size. These messages can actually take up a significant amount of network bandwidth, and this is especially true for switches that have many flow rules in its tables. As we previously discussed, the complexity of each flow rule affects the amount of control traffic needed to convey that flow rule to the controller. In the experiment, 100 flow rules were configured with varying levels of complexity, ranging from only matching a destination IP address to matching MAC addresses, IP addresses, and port values on both source and destinations. The amount of polling control traffic was captured, which represent the values in this figure. For the same number of flow rules on a switch, the amount of polling control traffic is very much dependent on flow rule configuration. As such, network operators should always keep this in mind and do the best to configure flow rules to be as simple as possible. In this experiment, we modified the size of a switch's flow tables and measured the amount of polling control traffic that was exchanged between the switch and the controller. As we can see in subfigure A, the relationship between polling control traffic throughput and flow table size is linear, and that most of the traffic is from the switch to the controller. This is because the controller only has to send requests to the switch, while the switch has to send increasing amounts of data as the size of the flow table grows. The reason for this linear growth in control traffic is because the switch has to send pretty much an entire copy of its entire flow table each time the controller makes these statistic requests. For a single switch with 500 simple flow rules, the control traffic throughput easily grows to 150 kilobits per second. In large networks with each switch generating 150 kilobits per second, this can be a significant problem. When there are many switches in the network, the total amount of control traffic that is generated can become large enough that some switches that are close to the controller will have to dedicate all of their resources just to switching control traffic only. We also collect and analyze other traffic metrics such as average packet size and packet rate. In subfigure B, we can see that the average packet size of traffic towards the controller is asymptotic and grows towards the NTU of the network, which in this case will be 1500 bytes per packet. And in subfigure C, we can see that the packet rate also grows at a linear rate with regards to flow table size. Though not discussed in this paper, Packet rate is a very important parameter for calculating packet latencies in switching systems. Next, we ran a similar experiment, but instead of modifying the size of the switch's flow tables, we modified the number of allocated queues on this switch. It is important to consider the effects of queue configurations, because in edge and fog networking bandwidth slide scenarios, there could potentially be many allocated queues that are used to schedule outbound traffic. In this scenario, the queue configuration control traffic must become significant and must be included in our calculations. As we can see, the control traffic throughput patterns are about the same as our previous experiment. The main difference is that the amount of control traffic throughput grows at a lesser rate than the previous experiment with flow rules. This is because it takes less data to transfer information about a queue than it does for a flow rule in these multi-part reply messages. Now that we have observed the effects on control traffic from flow rule configurations, flow table sizes, and queue table sizes, we can use those observations and analyses to generate a generalized mathematical model of control traffic throughput in software-defined networks. This model of control traffic throughput can be used in a wide variety of scenarios to accurately predict the amount of control traffic that will be present in the network at any time. For example, this model can be especially useful when planning large networks. This can be used to ensure that no single switch in the network will be overloaded with control traffic messages. Or this model can be used by SDN network controller to make predictions about network congestion and control message delivery speeds. In summary, it is very important to characterize SDN control traffic behaviors because control traffic can significantly affect network performance. For example, control traffic can potentially consume a significant portion of available bandwidth if the switches in the network are carelessly configured. We also demonstrated that the amount of control traffic is directly affected by the types of flow rule configurations, the number of configured flow rules on each switch, and the number of allocated queues. We then use these observations to generate a model of control traffic throughput that can be used to accurately predict the magnitude of control traffic in any network scenario. In summary, it is very important to characterize SDN control traffic behaviors because control traffic can significantly affect network performance. For example, control traffic can potentially consume a significant portion of available bandwidth if the switches in the network are carelessly configured. We also demonstrated that the amount of control traffic is directly affected by the types of flow rule configurations, the number of configured flow rules on each switch, and the number of allocated queues. We then use these observations to generate a model of control traffic throughput that can be used to accurately predict the magnitude of control traffic in any network scenario.